x, at x equal to 0, you have a barrier. That barrier is actually half, sorry, I beg your pardon. Right. The barrier is half m omega square a square. So this is alright? Okay. Now, you should all read Merz-Parker. This problem cannot actually be solved exactly. You have to use what is called WKB approximation, etc. But you can understand certain physical limits. Suppose A is equal to 0. Case 1, A is equal to 0. If A is equal to 0, then you have a single harmonic oscillator. It doesn't matter whether x is positive or negative. So, what are the eigenvalues of a single harmonic oscillators? You have En, where n goes from 0, 1, 2, 3, etc. These are quantum numbers, right? If A goes to infinity, okay, then you separate the two oscillators and they are far apart. Each oscillator will give you the same energy. So now, but you have two states for the same energy. So you have what is called a double degeneracy, right? A double degeneracy because you have two identical harmonic oscillators with the same energy. So therefore, now if you plot the energy eigenvalue as a function of A, and let me actually mimic Merz-Parker, you actually plot against square root 2m omega over h bar times A. And here what you plot in the y-axis is you renormalize this. So you actually plot the quantum number, which is En over h bar omega minus 1/2. So for n equal to 0, you see, so what you are plotting is this x value. Okay, for different values of A, alright? So when A is equal to 0, you are in this picture. You have a single harmonic oscillator, right? So you have one energy eigenvalue. So as I go along the y-axis at x equal to 0, I have n equal to 0, n equal to 1, n equal to 2, n equal to 3, etc. As A goes to infinity, we argued that you're going to get a double degeneracy because you have two independent harmonic oscillators. So Merz-Parker shows by using a WKB approximation that, so here is the, I have to be careful about this picture, yeah. So this thing goes down and merges here, and you have what are called collapse. You have these levels merge together. So for n equal to, here is n equal to 1, and n equal to 2, and n equal to 3, they merge together. So what this picture is showing is that how the energy eigenvalues are merging. For A equal to 0, you have non-degenerate discrete energy levels governed by this formula. When A goes to infinity, you have the same energy values again, but each energy value is associated with two quantum harmonic oscillators. So you have double degeneracy and then a merge. So if you are somewhere in between, you can see this tiny energy. And this tiny energy is in fact the difference between the symmetric and antisymmetric wave functions. Why? Because now you ask the question, how do I write the wave functions here?
This n equal to 0 state, at some position the energy is actually lower.
Yeah, that's because energy is, that's right. So what happens is that for n equal to 0, the energy becomes lower and then it's never negative though. It will become negative.
On h plus omega only, half h plus omega.
Yeah, but you are now in between. You have a complicated problem of two back-to-back harmonic oscillators. Energy is not negative, but it goes down below the ground state energy for the singularity for n equal to 0.
Because the omega changes.
Because of omega doesn't change, A changes. I'm copying it from Merzbach. So this is, I mean, again, it's not an exact solution using the WK, but I think I have not thought through why the energy becomes lower, but it becomes negative. Okay. So what are the wave functions? So as we said, now let's look at the case 1. For case 1, you have all studied a single harmonic oscillator, right? This is this problem now. For case 1, the ground state wave function is a Gaussian. This is called psi 0 of x. And I'm plotting it versus 2 m omega over h of x. The first excited state wave function for the harmonic oscillator has this structure. It's very similar to what you saw earlier. It's the antisymmetric part. This is the first excited state for a single harmonic oscillator. Okay. Now you combine the two. So now when you combine and you are in this model, then you find you can construct two wave functions. One is again psi 0, which is you have some symmetric combination, and then the other one so it turns out that these are the so basically these are what I have done is essentially the linear combinations of these two wave functions, and so now what I go to so if you think about this, how the merging is occurring, that you basically have, so in the case of a double oscillator, this wave function or the density means that you have equal probability of finding the particle either here or here. And in this case, it's the same, but except that this wave function is antisymmetric. Okay? So therefore, at this stage, you can also talk about what is called tunneling, because I must say that tunneling is actually an euphemism. It's the property of a quantum wave function. That is, suppose I prepare an initial wave packet which is localized here. This is the way you can do experiments. For instance, let's say hydrogen in niobium. The particle is initially localized in the left well, and if you let the system go, the wave function will start overlapping, like the picture we have drawn. And so there will be a probability of finding the tail of the wave function in this well also. So you will say the particle has tunneled. Classically, this behavior is prohibited because you have a barrier in between. But quantum mechanically, the wave function can leak, and because the barrier is not infinitely high. And if the wave function leaks, you have the possibility of tunneling. So how do we put all these things in a mathematical form? So let me go back to here. So now, I think this is something against which is something that Saurav has already introduced.
So can I just ask you one more question about this?
Yeah, just 1 second, let me get my thoughts right. Yeah. Right. Yeah.
So this double oscillator problem that you draw the picture, like when they overlap, so energy levels there's a sort of
The coalesce.
coalesce. So can one think of this the beginning of a band picture? Is there any way?
Yes, indeed. Indeed. We're going to come to that. That when you have, okay, by the way, what I did here is what is called linear combination of atomic orbitals, LCAR, right? And when you do LCAR for a many atomic system, you will see that for 2 atoms, you have lifted the degeneracy and you get 2 different energy levels. For 20 atoms, you go and read Kittel, here's a picture, that you have then this thing splitting into bands of 10 energy levels, for instance. So you have more and more atoms. You imagine Avogadro number of atoms, you have those many bands, precisely.
You call it LCAO.
I read in Kittel recently, and Kittel is a god. So maybe he has another name. He called it, I don't know what sort of linear combination of atomic orbital. Sorry, yes.
No, for physicists, orbital starts it off.
Was its spin. Then you go to n equal to 1. So n equal to 1 is already 2. N equal to 2 is 8. So you have 2s and 6p, right? 2n squared will give you 8. Now for sodium, so you have 11 electrons. So you have this 2 plus 8, which form this closed shell called the core electrons, and you have only 1 valence electron. Now, one thing that was not mentioned is, even for that single valence electron system, you have what's called a spin-orbit interaction, right? The spin-orbit interaction is a consequence of relativity and quantum mechanics. So, what did we learn in relativity? So, you have, let's say, a positive, this is something you will find even in Jackson's book. You have a positive nucleus, an electron, you have a Coulomb interaction. A Coulomb interaction means that you have an electrostatic field, an electric intensity E, along the direction joining the nucleus and the electron, right? But this is in the rest frame of the nucleus. The electron is moving, so it's a moving frame. It's a different Lorentz frame. So when you go to that Lorentz frame, that electric field will transform like a magnetic field, right? This magnetic field transforms, like H becomes, or B becomes V by C, the velocity of the electron with speed of light, across the electric field, the vector product. So it's a V by C cross E in the rest frame of the electron. But that electron is moving around in around its own axis called the spin. So that magnetic field, pseudo-magnetic field, will interact with the electron, giving rise to a Zeeman interaction, which is the spin sigma dotted with this V cross E over C, of course. This you can play with, interchange the vector product, and you get sigma dot L, the orbital angular momentum, because that electric field is a gradient of the Coulomb potential, so it gives an R vector or R unit vector. So that R vector, V and the sigma combining will give you sigma dot L. So that's the spin orbit interaction. And this is something that you have all seen in high school, in chemistry labs or in physics labs, that when you use sodium, you find in a Bunsen burner, you burn sodium, you see 2 spectral lines. What are these? 5890 angstrom and 5896. So why is this difference? This difference is because of the spin orbit interaction. So you see relativity happening in your laboratory. This the sodium doublet 5890 5896 is because of the spin orbit interaction. So what is happening is that if you have an electron in the p state, like L equal to 1, now you combine L equal to 1 with the spin S is equal to half for the electron. You have a total angular momentum J, which is vector L plus S, and you say that J can take values L plus S, L minus S. So L minus S is 1 minus half, which is half, and L plus S is 3 halves. So J is equal to either 3 halves or 1 half. You calculate L dot S as eigenvalue and you find the splitting, and that's the thing. So the splitting that appeared in Professor Pal's lecture in 2s and 2p, part of that is also due to spin orbit interaction. And it can happen even in a single electron system due to relativity. Of course, multi-electron system that he talked about will complicate the issue even further. So, so now spin. So we gave a long lecture on spin. So now how do I describe the spin operators? So quantum mechanics says that a spin is a vector, right? This has got three components, Sx, Sy, Sz, right? Now, why is it that I can't measure Sx, Sy and Sz simultaneously? If I have Px, Py, Pz, momentum, right? I have X, Y and Z, no problem. I can measure them simultaneously. Why?
They commute.
Huh? Batao?
They commute.
They commute, exactly. They all commute. Px commutes with Py, Pz, and X, Y and Z. Does Sx commute with Sy?
No.
Why not? What did I say, all these last 5 minutes? Huh? S equal to R cross P.
Because Lx and Ly do not commute.
Exactly. The reason they don't commute is because they're R cross P, and when you calculate, for instance, Sx would be the y component of R with the z component of P minus the other ones. Right? Now, if you take Sy, you'll get mixture of this X and P's, and they don't commute. Right? That's why they don't commute. So, he talked about commutation properties and simultaneity of eigenstates, right? Like the permutation operator commutes with the Hamiltonian, so they have simultaneous eigenstates. Simultaneous eigenstates means that you can measure both of them simultaneously. If they don't commute, you can't measure. So non-commutativity and non-measurability are connected. So you can't measure Sx, Sy and Sz simultaneously, and this fact is put in terms of a matrix representation, which is something in crash course again in 5 minutes that I want to give you, because we want to use this algebra for our purposes. So you take Sx, is this visible from the back? So Sx is h bar over 2, is a fundamental unit of the Planck constant, is a fundamental unit of angular momentum. Why? This is again R cross P. Remember, in the phase space, when you did either statistical mechanics or whatever, in the phase space, the phase volume dx dp is of the order of h bar. This is the old correspondence principle of quantum mechanics. Or if you put in dimension, you'll find that x and p product is the dimension of the Planck constant. So Sx has this structure, Sy has that structure, and Sz okay. So it is our convention that we say that I choose my Z as the axis of quantization. By the way, it is...
Sushanta, just one clarification.
Yes, please.
Whatever I was discussing, 2s2p degeneracy for hydrogen, etc.
Non-relativistic.
All non-relativistic. Right?
Correct.
That's a clarification of the students so that they don't get
Yeah.
confused.
So,
Then
but
later I said was non-relativistic Hamiltonian.
yeah. Yeah, but relativity is there in the lab, so you can't ignore it also. Therefore, I said that, yeah, absolutely correct. Absolutely. Whatever was discussed in the morning was on non-relativistic quantum mechanics. I just brought in relativity because I wanted to talk about spin. Somehow spin cannot be talked about without relativity also.
Yeah.
Fundamentally.
Spin has a